Hey, good morning, everyone. This is Anup Sarabu. I'm a senior technical product manager at T-Mobile. I lead initiatives around large-scale digital commerce systems that serve millions of customers across multiple platforms like web, mobile, and in-store. Today, I will share how observability is at core of making async event-driven commerce systems reliable and scalable. We will look at how we have approached this at T-Mobile, from architectural patterns to debugging techniques, and the key lessons we have learned along the way. Whether you're building distributed systems, managing reliability, or designing customer journeys, I hope this talk gives you practical takeaways you can apply to your own async environments. Let me start this with a statement. We are living in a world where milliseconds definitely matter. What is basically, let's say a customer is shopping on a website, and then while checking out, there's a delay, and then he can decide to abandon the cart, and then we can potentially lose that customer. We live in a world where conversion rates matter, and observability is no longer optional, it's foundational. Let me give you an overview of why we have to shift to async to really drive the omni-channel demands. To shift from sync to async, the thing that matters most to me is the observability, because that's the key of making the shift sustainable. Today digital shoppers, like I said, expect everything to be fast, personalized, and seamless, whether they're online or in store or mobile. The level of responsiveness pushes us to move away from synchronous architectures that block or fail under pressure. The challenge is, how do we maintain visibility and trust when everything runs asynchronously and independently? That's where observability becomes critical. It's our lens into this complex world. Synchronous systems are like daisy chains. One broken link, then everything falls or fails. When we switch to async, we get the scale of flexibility, but at the same time, we also lose the comfort of linear flows. Failures don't scream in async flows, but they just whisper. And if you're not listening to the right tools, you miss them. That's the trade off we must solve. Rise of asynchronous commerce. Why are we shifting from synchronous to asynchronous? The main reason is the demand and the personalization. Rise of headless microservices and event brokers. Omnichannel isn't just a buzzword, it's how customers behave now. I'll tell you an example. Someone browses on a mobile and then adds it to the cart, and then he walks into the store, and then he wanted to check it out with the agent. This means our system must be loosely coupled but tightly coordinated. Async communication helps achieve this, thanks to our microservices and event-driven designs. But now we need visibility across all those hops. And I'll give you an overview. I'll just explain a use case that we have implemented or that we are going to implement in T-Mobile. T-Mobile, the most busiest time in T-Mobile is during NPI. NPI is basically the new product launches, especially in September when Apple launches a device. We almost get 100K orders that day. That's the most busiest day for us than Thanksgiving or Christmas or New Year. And in one of the NPIs, I think last year, what happened in the first 15 minutes, because of the flush of orders, the payment system was down. And we were in a state where the orders were not submitted. Because today, what happens in T-Mobile is when you build a card, go to checkout, and then once you make the payment, then only you can submit an order. But because of it, like, we built circuit breakers which did not break the system as such. But what happened was, at least the payment was broken, and then the customers were struck there saying, hey, oops, something went wrong, and they were not able to submit the order. That made us think, do we really need payments to be synchronous? We can definitely go async as well. That's where we thought, hey, let's start. It's async is not something new. Today we already have this async for BOPIS. BOPIS is bring your own. So not bring your own. I'm sorry. BOPIS is buy online, pick up in store. At T-Mobile, we implemented event-driven architectures to support this BOPIS. And async, we are designing this, and probably by this NPI, we wanted to implement this async payment flow. These flows are unpredictable. A payment, like I said, a payment may succeed in 3 seconds or time out after 30. And then for BOPIS, inventory is critical thing, because inventory might change mid-transaction. So what we do for BOPIS is basically, again, to reserve, we make a soft reservation call for inventory. And then when customer walks into the store, we make a hard reservation call. So all of these calls are tightly coupled. That's when we thought, hey, let's do something async so that customers can be served in purpose. And then we had events to coordinate all of this. But it only works if we can see them happening in real time. What makes this async hard to observe? Regular synchronous calls, we can log their request response, or we can use a lot of tools and Splunk debug them. But async flows are invisible flows. We have tools there aren't really many tools that were and designed to support async. Imagine trying to follow up a story where each sentence is told by a different person at a different time. That's what it looks like debugging async flows. You don't know, there are a lot of events are coming up, and then you listen to the events and then you process the things. So the lack of casuality this caused that makes traditional monitoring ineffective. So we need tools to capture relationships, timing, and intent across systems. So to me, observability has 4 pillars. Distributed caching, distributed tracing. Distributed tracing is something you need to trace events across services using span correlations. You need to correlate them. And then event audits and replay. Reconstruct workflows for debugging and root cause analysis. When something goes wrong, right, you should be able to reconstruct the workflows and then debug and find an RCA. And then consistent monitoring. Validate that business outcomes are eventually completed. And we have a lot of domain dashboards which provide visibility using business-centric metrics and language. In async systems, right, observability isn't about tracking just technical metrics. It must reflect the business journey end to end. Here's how we approach it through our four key pillars. Distributed tracing. In T-Mobile, we use tools like, for distributed tracing, we use tools like OpenTelemetry to inject trace context into requests and events. This lets us correlate span across microservices even when communication is event-based. When something breaks, we can follow the trace path and pinpoint the exact hop where it failed or slowed down. It's a backbone for debugging async flows. Coming to event audits and replay, async flows don't leave a clean log thread. So we log constructed events with context, user ID, order ID, and sometimes timestamps, event type, etc. This allows us to replay what happened during an issue. Not only does this help with RCA, but we can also retry failed process without impacting other parts of the system. And for consistency monitoring, what we did was about validating the entire business transaction was completed. Not just the services are running. For example, an order placed. What happens when an order is placed? We reserve an inventory and payment is confirmed. And then whether shipment has been initiated or not. We track the completion of these workflows across time, services, and systems, even when events are out of order. Domain dashboards, we build dashboards that use business language orders, whether the pickup is done or not, whether the payment is in which state, whether it's in retry or not, whether inventory check has been done or not. These make observability actionable for non-engineers, like our product managers, support teams, and operations can understand what's going on without diving into logs and traces. So domain dashboards are really helpful to all the team members. Let me walk you over a BOPIS flow. This is what typically happens when customer places an order. What we do is we trigger an event to validate the inventory, and then we trigger events to notify store that, hey, an order is coming up, and then we trigger an event for pickup scheduling. These are all independent services working in parallel. Unlike if someone logs into tmobile.com and place an order, it's all one by one. Like basically once order is submitted, then the next step is payment is settled, and then after that it goes to the warehouse, and then warehouse takes its own sweet time to dispatch the item. But whereas in case of BOPIS, everything is async, like said, right from a payment is not async, sorry, and the event, the store notifications are async, the validations are async, and the pickup scheduling, everything is async. And for async payment, right, like I mentioned, while customer, like what the main problem that we faced during last NPI was orders were struck because the system was down because of an unexpected volume of orders. And then what we are thinking, how can we solve it? What we have been thinking is retrying is one option, but when the system is down, you can't even, that would not help. So what we are thinking is we want to decouple this payment processing from the order submission. So our plan was when the customer is present, when customer does a payment, since it takes longer than expected, so we wanted to put it on a queue and then process it asyncly. And then order submission also would be async. Only after the payment is successful, we will process the order. But let's say if the order is not successful, if the payment is not successful, then we want to trigger a notification to customer, send a text message or an email asking him to re-enter the payment, and only after the payment is confirmed, the order would be submitted. So this way, both the payment processing and the order submission are async. So we generate an order number and give it back to customer. Like customer doesn't know what's happening in the background. He just knows that, okay, an order is submitted, and he will get an email saying that, hey, your order is submitted and we are working on it. But in the background, we validate the payment, and if it goes through, then only we submit the order. But if the payment doesn't go through, then we again send a notification to customer to re-enter the card details. So this way, our customers are not blocked, and we are able to capture the orders and then process them. With async payments, the best thing is customers get an instant feedback. After the order is placed, behind the scenes, we check the card validity, and then we check for fraud, and we check whether the card has funds or not. And if something fails, we fall back without disrupting the user flow. Here, observability means monitoring the status queues, tracing failures, and ensuring consistency without sacrificing speed. So I think we spoke a lot about async. We really need tools and techniques through which we can trace them. I'll go through few tools that we use at T-Mobile to track these events. OpenTelemetry. OpenTelemetry is used to capture and correlate spans across distributed services and events. So this is our go-to standard for distributed tracing. It allows us to inject trace IDs and span context into each service call and event message, even when systems communicate asynchronously. Whether it's an API call or an internal microservice call or a Kafka message, we tie them all back to a single customer transaction. This is critical for finding out what went wrong, especially in complex flows when something goes wrong. We use a lot of, if we have a lot of tools into the way we monitor OpenTelemetry. We have SDKs. We like in web, like in UI, we use Node.js and Java, Python, etc. And then at commerce system, we use Datahog, we use Jagger, we have Grafana. Grafana is actually a lot for our backend services that we use. And then sometimes if the services are hosted on AWS, we use AWS X-Ray. And then for Kafka, like Kafka is actually central to our async architecture because it acts as backbone for our event transport. But here also what matters is observability. So how we monitor, what we monitor, we monitor the queue depth to detect the backlogs, and the consumer lag to catch up slow or stalled services, and then the throughput, like to understand how much is a system load. So what tools we use here is Kafka Manager. It manages the topics, the queues, and also the clusters. It's deprecated, I know, but we used to use it. Now we also use Grafana to do a visualization of Kafka throughput and partition lag and message drops. And then we use Burrow, a consumer lag monitoring tool for Kafka. Error rates for retries to catch failing event handlers. These metrics help us to detect not just failures, but also performance degradation before it impacts users. And custom event replay dashboards. These dashboards are our internal dashboards which help to track an order from end to end, right from adding the service to the cart until it's checked out. Again, we use Kibana here, we use Metabase, and then we use Power BI, and then we use Grafana also. What are the sources for this? We use business events that are business event logs from Kafka consumers or event gateways, and then we use telemetry systems, all of this. And how do I measure success? When I move from sync to async, how do I measure the success? The success is basically today we support about on average, we have about 7 million customers logging into tmobile.com. Like we registered those many number of tokens. But eventually when you look at the cards, so from 7 million, only 130K cards are being created. Okay. And out of 130K, the actual orders come down to 35K. But when we used async things, what we have seen, if we look at the BOPIS orders, we have seen the checkout rate, like let's say out of those 130K to 30K, it's almost 1:4 ratio. But if we look out, the BOPIS orders are more faster checkout. Like it's not 1:4, it's 3:4. Like out of let's say we had 1,000 orders, so the BOPIS cards that are built are only 4,000. This led us to lower abandonment. The BOPIS was on BOPIS. If I see, I can trace that the card to order conversion rate is significantly higher in case of BOPIS. And then what happened with async, we are during the peak time, like I said, NPI, we are 97% available. So even promotional peaks, sometimes we give promotions saying that, hey, buy one, get one, or to attract customers saying that, hey, you're porting and you get these offers. So even when we announce those promotional things, though at that times also we were almost close to 100% available. You see the results speak themselves. Faster checkouts mean higher conversion, and lower abandon rate shows how improved trust. And high uptime during traffic spikes proves that resilience and scalability can go hand in hand if observability is right. I think you have to, when you move from sync to async, right, you have to do some trade-offs. I hope you all know what this CAP theorem is. Cap theorem is C for consistency. Every read returns the most recent write. Okay. Availability. Every request receives a response. And then partition tolerance. System continues to operate despite network failures. Yeah, you'll have to trade off. When you have to be consistent, then your availability might be lost. If you're on a synchronous systems, you will be consistent because you wait for it. So it takes 10 seconds or 15 seconds, you'll get the response back and the customer is present. So it is very much consistent, but availability, right? Like I said, during peak time, gone. Like if you're bombarding it with a lot of requests, then the system is gone. But when you move from sync to async, consistency, I would not say you'll have to 100% compromise, but you might have to make a little compromise. Like I said, BOP is right. So since we do everything asynchronously, what happens? Customer added a device and an accessory, and then he submitted an order. But by the time he come to the store, if within the store, if there are no accessories, then we have to trade off saying that, hey, you can only buy a device because this accessory went out of stock. It's a little inconsistent, but still we try to again keep up the inventory up to date and make sure that the customer gets what he orders for. But again, you'll have to trade off between availability versus consistency. And then what we do, and in our solution, when we move from sync to async, the important thing is idempotency. When we make sure if some failure happens, we have to suppress this duplicate side effects. Let's say if payment failed, then you shouldn't continuously charge customer. You should not charge 3 times. Make sure that if customer is charged once, then you don't charge him at all. And then versioning, tracking changes and ensuring correct state resolution. And then compensating transactions. So if something goes wrong, then we undo or mitigate the failed steps. One of the core trade-offs in distributed systems is explained very well by this cap theorem. It tells us we can only choose between 2 of 3 guarantees. Like either if you want to, out of these 3, right, the consistency, availability, partition tolerance, you can only choose 2 between sync versus async. If it is sync, then it is consistent and it is partition tolerant. But if it is async, then it's available and then partition tolerance. And in a high scale event-driven commerce, partition tolerance is non-negotiable. Failures will happen. So we typically prioritize availability, meaning we must relax strict consistency. This leads to eventual consistency. Data will converge, but not instantly. To manage this effectively, we, like I said, we use a lot of techniques. We design the services that are idempotent so that repeated events don't cause duplicate effects. For example, if payment confirmation is sent twice, it shouldn't charge the customer again. We ensure that the retries are safe. And then versioning, we attach version numbers to entities like orders or payments. This helps us detect and resolve race conditions. If 2 systems try to update the same entity simultaneously, the version ensures only the correct one is applied. And then compensating transactions, when things go wrong, we don't roll back. Instead we emit events to undo the mitigation issues. For example, if an order was confirmed but payment later failed, we emit a cancellation event and restore inventory. Like I said, observability plays a critical role here. It alerts us when events fail out of sync, retries are piling up, or state transitions don't complete. Without the visibility, we wouldn't know consistency is broken until a customer complains. With it, we can react in near real time and fix issues proactively. Now, how do we really test the async systems? How do we simulate delays? How do we simulate message losses? How do we take an action to restart them? How do we again validate retry logic, fallbacks, and idempotency? Focus again, monitoring. How do we monitor the queue depth? How do we monitor detect the backlogs? How do we latency? How do we track the delays? And then how do we make sure the event sequences are correct and complete? Now, testing asynchronous systems is fundamentally different from traditional applications. It's not just checking about individual service or APIs. It's about testing the system behavior over time, under pressure, and across boundaries. Let's break it down. Simulated failures. We simulate the real world scenario, such as delayed customers. What happens if a service is slow, or if the service is slow to process a message? And then what happens if the message is lost? What if event never reaches its destination due to a transient outage? And then service restarts. Let's say, how does the system behave when one component resets mid-event? This helps validate our retry, deduplication, and fallback mechanisms actually work in the practice. These things work in practice, but not in theory. Monitoring essentials. Async observability means watching the systems as connected graph of event flows, not isolated services. We focus on queue depth and where large backlogs may indicate slow consumers or broken processors. Processing latency. Now, are events being handled with acceptable time windows? If not, where's the bottleneck? Casual change. We can trace a customer's order from placement to fulfillment. Missing links could mean dropped events or unhandled failures. A common pitfall is thinking a green dashboard means everything is okay, and in async systems, services might be up but flow is broken. That's why we don't just test endpoints, we test the system end to end. What lessons we have learned when we implemented async? I'll wrap up the major lessons that we have learned from building, scaling async commerce systems. Design for traceability. So now I always emphasize this. You have to, when you're building the system, you build the design on how you want to trace them. Tracing isn't something you can bolt on later. Most of the things we feel that let's implement the design and then tracing can be done later. But for async, I would recommend first you think of tracing. How do you want to trace the events? And then it has to be intentional. This means using consistent trace IDs, structured logging, and and propagating context across services and event handlers from the start. If you skip this early, you will struggle, debug, monitor, and support your systems as it goes. Trust me, it's very hard if you wanted to think about tracing at the end. So always design looking at how we want to trace them. And then accept and plan for eventual consistency. In distributed systems, chasing perfect real-time consistency will hurt your availability and scalability. Instead, we have learned to embrace eventual consistency and engineer around it using strategies like retries, idempotent operations, compensating transactions. Observability is what keeps us honest there. It lets us know when consistency breaks and help us to fix it proactively. Again, I would say align metrics to business events. This is key for making observability useful beyond engineering. Developers care about logs, spans, and error rates, but product managers and support teams care about orders, not shipping payments stuck in retry or event or syncing. So building dashboards and alerts that help speak up the language. It shows how you turn observability from a dev tool into an organizational asset. I would like to conclude saying that async commerce architectures give us what modern demand: scalability, flexibility, and resilience. They allow different parts of the business to move at their own pace. Orders can be taken while payments are still processing, inventory can update independently, and notifications can be retried without blocking the user. But here's the catch. What that flexibility comes, it comes with a complexity. Things happen in parallel in different systems at unpredictable times. If we can't see across these flows, we are flying by it. That's why observability isn't just a technical layer, it's a strategic enabler. It's what allows us to build fast, recover faster, and continuously improve. When observability is built, we don't want just to operate, we understand when something broke, why it broke, and what to do next. That's how we maintain trust in the customer experience, even when the backend gets messy. So as we build asynchronous commerce event-driven systems, let's make sure observability stays a first-class citizen. It's the difference between hoping things work and knowing they do. And thank you very much for patiently listening on this. And please let me know, like when you're building anything async, I'm happy to help. And I hope this session gives you practical insights about building and operating async commerce systems with confidence. And if you're working on similar architectures or facing any challenges, I would love to continue this conversation. Feel free to reach me via email or connect me on LinkedIn. Thank you. Bye bye. Have a good day.